Welcome everyone. This is the third lecture of our computer vision course. Today I'm going to show you the Hough transform. So my original plan was to show you today histogram-based algorithms, but I've decided to switch with the Hough transform because there is a nicer fit with the edge detection algorithms that we looked at last week. So in last week's lecture, we looked at how to detect, and thinnen and track edges with the Kenny edge detector. So an input image like that would be transformed to a binary image that has ones at those image positions where we have borders or edges and zeros, L's. And today, the so-called Hough transform will be used to fit objects, for example, circles or lines or other like shape primitives, to these edge images. The Hough transform is called Hough transform because it was published by Paul Hough as a US patent in 1962. And the original formulation was a little extended by Duda and Hart, two famous machine learning people, by the way, just 10 years later. And that is the way we typically implement the original Hough transform. So today we're going to look at exactly how this original formulation of the Hough transform works. So the Hough transform robustly finds simple shapes in edge images, like this one here. And robustly means that even with missing edge pixels, like here this upper arc of the iris of the eye, or even with image noise or so edge pixels that show up although there is no edge, or real edges that do not show up or show up somewhere else. The Hough transform really is robust against these natural variations in edge images. And it's usually used for simple objects, so lines and circles and even ellipses, and can be used for really any model that you have that has parameters, right? So if you have an equation that describes the shape or even the motion of an object, you can use Hough, and I'll show you a couple of examples later. We'll also go in the second part of the lecture to the so-called generalized Hough transform that can be used for any non-parametric model, any shape, given a template. Okay, so the intuition behind Hough is that multiple hypotheses that exist can be supported and voted for by the edge pixels. So that these blue circles here, edge pixels, and now think of different hypotheses of circles or ellipses that would that would produce these edge pixels, right? So if we had an image structure that is similar to this red circle here, we could find edge pixels at these locations, and the other way around, by seeing only these edge pixels, the first hypothesis would be supported with 4 votes, right? But that doesn't make it right per se, because other hypotheses, like this blue or this green circle here, would also be supported by these edge pixels, although with a lower vote count. Yeah, so we think of this score or edge score, and we could list our hypotheses here and sort them by how many edges these hypotheses are supported by. Yeah, and we can do that because single edge pixels really support multiple hypotheses. Okay, and by collecting and voting for all the different hypotheses that every edge pixel supports, in the end we hope to find a maximum and a respective hypothesis that is then the most likely explanation for our edge image. Okay, so let's apply this idea to the simplest geometric object, a line. And to be able to create different hypotheses, we need a description, a mathematical description of a line equation. So what is your favorite line equation? Well, I hope something like that would be a response. So let's just dissect this a little bit. The y value, along that line is basically a sum of two parts. One is that constant offset n, and a second part that grows with x, mx, let's say. Okay, and this is the remaining part on top of the n, and we can think of that position as x equals 1, so that surplus onto n is basically that parameter m. And what does that mean? Well, it's basically saying that's how steep that line is going up over 1 unit step in x. So m is the slope. And now tell me a question for the Q&A session on Wednesday. What would be valid parameters for a vertical line, right? So a line that's basically somewhere, maybe on the y-axis, maybe somewhere else, right? So we probably will find lines in our images. And so what do you think would be valid parameters? I'm curious to hear your solutions. For now, let's look at another way to describe a line with the Hesse normal form. It reads r equals x cosine alpha plus y sine alpha. And you can think of this line equation again as having two parameters, but these are r and alpha, r being the distance from the line to the origin of the coordinate system, and alpha as the angle of this orthogonal vector here, of this orange vector. So to understand that line equation, you have to understand what the dot product actually is. It will be your best friend probably forever, because it shows up in computer vision, in machine learning, in so many topics, and it's so fundamental. I had to create this extra slide here. So the dot product between two vectors is a scalar value. That's why in German we call it Skalarprodukt, yeah? Scalar product. So let's think of Q as a unit vector. So length of Q is 1. Then this dot product here results in a number that is basically the orthogonal projection of this vector x onto this vector q. Okay, so that gives us the length of the projection. Okay, so why do I mention that? Well, think of cosine alpha and sine alpha as a unit vector into the direction of this orange vector here, but it has unit length, right? And now this would be our q, and x and y are now arbitrary points in the image plane. And by taking the dot product, we obtain a number, and if that number is r, then this position in the image is a valid solution for the line equation, right? So could be this vector here, could be that vector here, but it has to have the same projection length r. Okay. You can now think of a line in the image to be represented by two numbers, the r and the alpha. So one line in the image corresponds to one point in parameter space. Yeah, for example, a certain value for alpha, let's say 80 degrees or something, and I don't know, 20 pixels a distance to the origin, that is your configuration of that line here. And another line, would have obviously different set of parameters, like this alpha, like 45 degrees, but a longer distance r to the origin. And maybe that line has a long, alpha, which would show up here, but a very short r. Okay. And now think of an edge pixel that we observe as support for an infinite number of lines, right? So that edge pixel could be, resulting from virtually all possible lines. And all possible lines now have all possible combinations of r and alpha that, go through that point. And that is basically a curve in parameter space. Okay? So what if we had two edge pixels? Well, for all the lines going through that one blue edge pixel here, we have a curve through parameter space, one of these combinations for each of these lines, but also we have a bundle of lines going through the second pixel, and these lines are not the same lines as the blue ones, so we have a separate curve, this orange curve, through parameter space. But comparing those two bundles, we find exactly one line that is the same, right? That is going through both of these edge pixels. And this line now, need to be represented by the same set of parameters, r and alpha, and that is both curves in parameter space need to overlap, okay, need to intersect at these points. Okay, so the points in parameter space where the curves cross, where they intersect, these points represent this line through both edge pixels. Now, how many solutions are there? Another question for our Q&A session. Good. But the parameter space now is in a continuous space, and in the computer, we need a discretized representation, and we, for the lecture, will call this the accumulator, because it will accumulate, it will collect the votes for specific hypotheses, right? And the algorithm is pretty simple. For each edge pixel in our binary edge image at a position xy, we iterate over all different discrete angles alpha, let's say from 0 to pi, question why not 2 pi, and then we'll plug this into our cosine and sine, so we'll obtain that unit vector that points into the direction of alpha, and then we multiply that by our edge position, and we obtain an r distance from the origin for that specific line, and we increment the accumulator, which is a 2D matrix, right? So we have 2 dimensions, r and alpha. We increment that specific position in the accumulator. And by doing that for all the edge pixels that we have, we'll basically paint the curves in the accumulator. And all those positions where we, all those positions in the accumulator at A and R that have high values, these positions, these parameter configurations, are those that are supported by many edge pixels. Okay? And what we then do is clear, we just find the local maxima in A to obtain a set of lines that are highly likely, okay, that are supported by the most edges. And we can apply this idea to any other shape for which we have an equation, for example, to circles. So the circle equation reads like this, but it's basically, so for a moment, disregard the xc and the yc. What the circle is that its coordinates of the contour should have the same, constant distance to the origin, right? Which would be r. And so that's basically applying the Pythagorean theorem, which states that in this kind of triangle here, the x and y coordinates are the sides of this triangle. So if we square and sum these up, we get the r, so the hypotenuse squared. And that's exactly what this equation shows. Now, if we have a non-zero center point, we basically subtract these from the x and y coordinates of the contour, and then we get this equation. Now, this equation has 3 parameters: the center of the circle and the radius, so the distance of the contour pixel to the center of the circle, and so we need 3 dimensions for the accumulator. Now, in the line version, we iterated over one of the parameters, the angle, right? So from 0 degrees to pi to 180 degrees. And by using this assumed orientation, we then plugged this into the equation, and then we found the distance of the line, right, to the origin. And we knew where to increment in the accumulator. Now here, using just one parameter won't work. Yeah, we need to use both. So we basically run through all possible center locations. And now, if we have an edge pixel and we assume the circle to be here, then the distance of both gives us directly the radius, and then we can access that location in the accumulator and increment it there. So, and of course, we can have more complex shapes like ellipses, for example. And the question now is, how many parameters do we need to describe an ellipse? So an example of the Hough transform in action in real research is this paper in which we looked at how the honeybee moves their antennae in memory formation and memory consolidation. And so the Hough transform worked beautifully. It was fast, and so yeah, read about that in the paper. And in another project, we used the Hough transform not to detect circles or lines, but to match the motion of those points. See those points here? we try to match a rigid transform motion model, which is just a rotation and translation, right? So 3 parameters, and to find the maximum amount of these points that do that kind of rigid motion, to then identify the location of a bee that is dancing, and also to follow her movements. So in your assignment, we want you to implement the Hough transform for lines or circles. Obviously, you can do both if you like. We'll provide 2 sets of data, one showing those beautiful eyes, and the other set, those camera feeds from within a car. Okay, so for the remainder of this lecture, I want to show you the generalized Hough transform. It was published by Ballard in 1980, so still quite a while ago. But I think it's a perfect, completion of this idea of, matching shape or other patterns, models against an edge image. So when you use Hough transform or the generalized Hough transform, well, think of detection or location tasks where the shapes aren't simple lines or circles. For example, here in this animal picture, if I asked you to find a specific bat, you might take a while to actually find it. Let me see. I think, oh yeah, I know what it is. Here it is, yeah? But I knew before, so I don't know how long you would take. Let's go through it step by step. The first step is to take your template, that's what you have to have, and pre-process it in the following way. So let this be our shape, and we first have to run our Kenny edge detection, because we need to have the contour of it. Okay. Now we'll then iterate over all edge pixels and compute the center location. Okay, so that's the object center C here. And then for any given point on the contour, we need the gradient. We need its gradient. Okay, and since Kenny already computes the image derivatives, we can get this image gradient G, or the direction, the angle of G, with no additional cost. And we do that for all points on the contour. We then calculate the relative location of that point P, the relative location of the center of the object from the perspective of point P. And we'll then iterate over all of those contour pixels and add these vectors vi into a table. Now we do that discretizing the angle theta in a certain amount of steps. Let's say every 20 or so degrees we'll use another bin. And so, for example, here V1 and V2 are on the same kind of gradient direction. That's why we put them in here, although 20 degrees doesn't seem right. And then V3, for example, is added in another bin here. And we do that for all the contour pixels and all the gradient directions and location vectors of C. Okay, so how do we use the R table now to localize the object in a new image? Okay, let's first look at this edge pixel here. It has a gradient orientation. Now, given the gradient orientation, we can think of this pixel to be on this edge of our object at that specific location, and that would indicate the center of the object to be here. Now, but it could also be that the same pixel now is on another location on the same edge of the object. So, for example, here the green shape shifted downwards, so the edge pixel it's then on this upper location here on the same edge, and the center location now would be obviously shifted downwards as well. So one edge pixel supports many different hypotheses, just like in the original Hough transform. Now to find your object, you use another accumulator. Again, this is just an image matrix, the same size of the image, for example. It could be smaller, then we have to save some space, and sometimes you don't need that kind of accuracy. But let's think of this just to be an image. So for each edge pixel that you encounter in the let's call it haystack, okay? That's where you want to find your needle. For each of these edge pixels, you look up that line in the R table that corresponds to that gradient direction, and then you take that list, add these vectors. Remember, these were relative, so relative to the location of the pixel. So you add these vectors on to the location of the edge pixel, and then you end up incrementing accumulator positions for each of these entries in the list. You increment it by 1, and then you see at some positions these vectors overlap onto the same accumulator position, and that's where you increment not just once, but how many times it overlaps. So, for example, 3 times, like here. So, but that wouldn't work if you had differently scaled object, right? So think of your object's template not having the same size as then those objects that appear in your haystack image, or the other way around, right? It doesn't really matter. In the end, you have vectors pointing to locations that don't make sense, because those edge pixels that you observe are, either like here on the contour of a smaller version of the object, or on the contour of a larger version of the object. So they either overlap wrongly in the accumulator, or they even don't overlap. So what can we do? So take, for example, just 2 edge points, and they're pointing to the center in the template, but then you have your object in double the size. So those center point vectors do not even overlap. They don't hit the correct point, the correct center point. So what you can do is then assume a certain scale of the object. So for example, scale 2, and scale those vectors, which would end up in them overlapping at the correct location. You don't know a priori what different scales you can expect. So what you would do is you have your accumulator and you discretize your scale for a number of reasonable, feasible scales. So for example, from 0.5 to 2, right, in 10% steps or so. So that basically means for us, we do have another accumulator dimension, which used to be 2-dimensional for x and y, and now we have the 3rd dimension for the scale, right? So, for example, for one scale level, those vectors are that long, and then for the next scale level, those vectors are scaled. Okay? But what about rotation? We want the algorithm to find rotated versions of the same template as well, not just differently scaled ones. So, for example, here, the original unrotated version has those edge pixels here with their respective gradient directions, and the rotated version obviously comes with the same pixels, in different locations. They too have gradient directions, but they are rotated about the same angle as the original object. Those vectors pointing to the center, again, are also rotated by the same angle. So observing an edge pixel with a gradient orientation of, let's say, 90 degrees leaves us with the question, okay, is this maybe that pixel on the unrotated, the original version of the shape, or is it maybe another pixel, on this location on a rotated version of the shape? Each of these hypotheses would point would put the center in different locations. So let's say we have observed an edge pixel with a gradient orientation of 170 degrees. Now, we would, in the original version, or in the original formulation, assume the object hasn't been rotated, so we look up the list of v's in this line corresponding to that gradient orientation, and these are these 4 yellow vectors. Now, if we observe a 90 degrees edge pixel, for example, and we assume the object has been rotated by minus 80 degrees, so clockwise around 80 degrees, we would not look up the 90 degrees line here. We would look up, the original orientation, which would be 170, right? So 170 minus 80 is 90. Okay, so objects that originally had a gradient direction of 170 would appear as 90 degrees, or those pixels would be, those edges would be observed as 90 degrees. Okay, so we look up those now, those those center locations, V or VI. But now, in the original R table, they just are the same ones as we had here before, and they do not point to the correct locations. We have to rotate them as well by the assumed rotation. And these ones would be the correct ones. So following the same strategy like seen with scale, we add another dimension to our accumulator, which was previously 3-dimensional, now it's 4-dimensional for the different assumed rotations. Okay, and here, for example, for a 10 degrees discretization, we would have 36 for the whole 360, blocks of accumulators, each block for one assumed orientation. So that is an example I found on YouTube. Here, this bottle is this shape that we look for, and you can see that's the accumulator. It's tracked fairly well. That's the gradient direction, and it seems really to work well. Okay, so for you, I have thought out this this problem. So the one that we introduced you to on the very first slide for this algorithm, find the bat or find any other animal that you like, and also adding scale and rotation invariance, you can find Italy. Okay. Okay, that was it. Let's summarize. So I showed you the classical Hough transform for finding shapes for which we have an analytic parametric description, an equation that describes where in the image, in what kind of orientation and configuration you would find edge pixels. The more parameters, though, this parametric form uses, the more dimensions we have to create in the accumulator, which needs more space to store these entries and also more time to loop through you know, those dimensions actually. But it is very robust. People still use it for a variety of problems, and well, that's why I chose this algorithm here for this course. The generalized Hough transform is used to find more complex shapes, although obviously you can even use it for finding circles or ellipses if you want. There's no need for a parametric model anymore. You have to have a template though, and do a pre-processing step as discussed. You at least have 2 dimensions for the accumulator, which is the most of the time the image dimensions. By adding rotation invariance and scale invariance, you add 2 more dimensions, making the accumulator 4-dimensional. Okay, so that was it. I hope you enjoyed Hough transforms. Looking forward to hearing your questions. See you all on Wednesday. Ciao.